All right, welcome to Computer Science 305. This is the second part of the object-oriented talk. In this part, we'll talk about several well-known object-oriented features, including classes, prototypes, inheritance, encapsulation, polymorphism. And so, the first thing is classes, right? If you programmed in Python, you programmed in Java or C# or C++, you know about classes. All these languages that I just mentioned are class-based object-oriented languages, right? And this class construct has a lot of different purposes. First off, it gives us a structure in which we can group our fields and methods together. It gives us something that we can instantiate, right? The whole point of the class is that we can use it as the cookie cutter, if you will, from which we form instances or objects, right? And we can then create as many as we need. And they always start out by calling some method that sets up that instance with initial values, right? We call that the constructor. Furthermore, classes give us a way of creating inheritance hierarchies, right? We can modular at a very fine-grained approach. We can modularize our code, right? Break out functionality in several small pieces that, when put together at runtime, form large objects themselves. And further, this also gives us the capability to move things up and then follow what's called the dry principle, the do not repeat yourself. So we can move common things up in the hierarchy and move them to more abstract locations, such that we can guarantee that everything will have this. We only have one place to maintain if we need to. Classes also give us the construct of type, right? Objects or references to them have a class, superclass name as their static type, right? Classes also give us a place to store class-based information or static or information specific to the type rather than to an instance of the type. We call in Java we use the keyword static to denote this. So fields and methods, one per class if they are static, right? They're not associated with an instance. Classes also give us a fine-grained form of namespacing, right? Typically in languages like .NET and Java, we have like package or namespace structures that contain classes themselves, but the class also acts as its own namespace for its fields, for its methods. And so it gives us a way to, localize access to these things through either variable names or class names, depending on if they're static, if they're instance or static based. So, but there's also the capability for object-oriented system to be based to not be based on classes. And when we start doing this, right, this leads us to all sorts of weird issues. Like, if you don't have a class, how do you actually create an instance? Well, we do that by essentially constructing the object straight up every single time by listing all of its methods and fields on the spot. Or we can take a prototype. We create a prototype in memory, right? During runtime, we construct a prototype, and then we keep cloning it over and over, and we modify it after we clone it. And so, for example, right, we think about a normal class instantiation in Java, right? X equals new stack, right? But we could also create a new stack by, if we didn't have classes, by simply constructing the object straight up, where for example, in a language like Self or JavaScript, which is also a prototype-based system, we can just use what they call the JavaScript object notation approach, construct a listing of the fields and methods inside of the actual a set of curly braces. And all of a sudden, that's an object now. We can access those things just like we normally could. We say x dot top, x dot has more, and would do everything as we expected. Furthermore, if we've created one, like let's say we created one an actual class just like we created x here, but we call it y, and I need to make a new x, I can just say y dot clone, and or some other way of doing it, and that will produce a copy of y, and we can then modify that as necessary to construct the new, to modify x by setting up its values for its fields, by adding new methods as necessary. So this becomes a very interesting approach to handling object-oriented systems. Very few languages have actually been implemented as prototype-based systems. I would say the most well-known would be JavaScript. But basically, a prototype is just some object that is copied to make similar objects, right? It's a prototype. It's like a class, but instead of a class is a thing defined in a file that has nothing to do with, it has no values associated with it, from which we must instantiate using a special method. Whereas a prototype is something that we construct in memory in real time that we then have to make copies of to adjust and create new objects from which those objects can be adjusted by removing and adding things as necessary. Prototype languages like Self use this concept instead of classes. It tends to be a little more difficult to really understand how it's working when you do this, but it can be done. Now, as I've said, when you don't have classes, in a class-based system, we use instantiation, and it's the only way to use classes. Let me rephrase that. It's only one use of classes. When you're in a prototype language, we lose things like type information. Prototype-based languages are always dynamically typed. We also lose inheritance, right? Prototype-based languages use instead of having inheritance, it uses delegation, right? So, we make a copy of a given prototype, and thus, when we do that, we're delegating any calls on that object to the prototype itself. So, or wherever we gained the method from, right? So if we add new methods right there into the new object that we copied from the prototype, if we make a call on that method, it goes to that method that we define there. But anything else will be delegated back to the prototype from which we copied. So bear that in mind. Inheritance itself, right? When we in a class-based system, inheritance is really simple to think about, right? It's just a relationship between two classes, where one derives from another, right? So we have a class that we derive from a base class. The derived class acquires fields and methods from its base class. The question becomes, what do we actually get? And this becomes language dependent. And it's almost, I would say that there's really no common concept of what we would gain through inheritance. So one of the things is, and we have certain questions surrounding inheritance, right? Is there the capability to have more than one base class? Do we have to inherit everything? Now, in things like, for the first question, in languages like Smalltalk and Java, there's only one way of doing it. And you can only inherit from one single base class. And this is through, in Java, this is what we call the extends keyword, right? We have that base class. We can also implement interfaces, but that's not inheritance in the same way. That's realization. It's a different concept. But in languages like C++, Eiffel, or the Common Lisp object system, we have the capability to have multiple inheritance, multiple classes we can inherit from. When it comes to the, are we forced to inherit everything? Well, in Java, we can actually prevent from inheriting everything. We can call things final, like methods. We can inherit. We cannot necessarily override. That would be the barrier. And I would like to say that we don't inherit everything in Java. That depends on the accessibility of those things. But in essence, we gain everything because how inheritance really works in Java is that we construct our object and it just has everything available to it from all of its other classes, and thus passes type information at the same time. On the other hand, in languages like Sather, which is mentioned here, derived classes can rename inherited methods, right? which allows us to handle multiple inheritance. But you can also undefine certain methods, so as if they're not a part of that class, and thus we did not inherit them. Furthermore, sometimes we have to ask ourselves the question of, when we're looking at language, is there a universal base class, right? So in order for Java to really be consistent, they made it so that they had this, and to allow certain things like automatic string coercion to occur, they said we must have a base class from which everything inherits, which we call object. In C++, that's not quite the case. Furthermore, is a specification, right? So, can we force on an object that it will have certain methods? In Java, we can do that, but and the only thing that we get is method obligations. But at the same time, we can have certain in Eiffel, for example, we can have invariants, which are constraints placed on a class that we can actually inherit, reducing down, like, for example, what types of values they can actually have. It must, for example, a method may not be able to return null, or the type itself may not be nullable. We can force invariants like that on a class, and that can actually be inherited, or can be even further specified. We also ask ourselves, are the types available? So in Java, right, anytime you extend a class, that the class that you're defining is also of that same type it's extending, which is also of the other type, right? And so we inherit that all the way down through the inheritance hierarchy. This becomes like, is the capability to override or hide things that we inherit, right? So in Java, we can access, from our constructor, we can access base constructors with the keyword super and in parentheses, and then we can put parentheses after it as our first line of our constructor, and we can access the base class's constructor. We can also use super to access base class fields and methods. And now the interesting thing is, if we define a field in our class that has the same name as a base class's field, or any other class above that, the class we're defining in the inheritance hierarchy, we can actually override. We're shadowing those fields, right? And so if we need access to those fields, we can just use the super keyword. It's similar to using this, only it accesses up through the inheritance hierarchy. Similarly, if we override a method, right, in Java from one of our base classes, what we'll end up doing is, if we need to access the version from previous that we would have normally inherited, we can call super and then give it the method name, and then it will actually call that over the method that we're overriding. So if we have certain functionality we need from that we're now just modifying, we can add that in there, and you can do that anywhere inside the method definition. At the same time, we can prevent from overriding a method by using the final keyword. If we call a method final, then it can never be overridden in one of its base class in a base class. The last version is in the actual superclass, where it's defined as final. But all these constructs are dependent on the language. Like, even how you do this is dependent on the language, or if you can. Some languages, like .NET languages, you do not necessarily have the capability to override unless their method is defined abstract or virtual. So bear that in mind. Encapsulation is a key component of any object-oriented system. Encapsulation just gives us the ability to control access to data, right? And so what we want to do is, the basic concept is, we encapsulate as much as we can. We encapsulate data and then provide a controlled interface through which that data can be manipulated. but only in the way that the class allows. And so objects are the basis for encapsulation, and how that's done is dependent on languages. In most languages like Java, C#, Smalltalk, Self, JavaScript now, and Python, Ruby, we have these what we call accessibility modifiers for methods, classes, sometimes even namespaces, modules, all these different things, and then inside them, their fields and their methods can be set up such that you can say, well, who has access to what? And so if we take our fields and we privatize them or protect them, in the case of Java, then we're controlling who has access. And so in Java, we have 4 levels. Private, protected, and public are well known. And then there's, when we don't provide an access modifier at all, that's the default. And so private means only that class has access to that thing, whether it's a field or a method. It is not accessible by any class that inherits from that class or any other class defined in the system. And so, and then you have default, which says whatever doesn't have an actual available or defined accessibility modifier can only be accessed by that class, the class in which it's defined, or any other class within the immediate namespace or package, right? Not in any package, subpackage thereof, only in that package. And so that means if you define subclasses, but outside of that package, they do not have access to that field or method. Protected, on the other hand, allows that class to have access to it, anything in the same package as that class, or any derivatives of that class. So, and then finally, public is just accessible by everything. Some languages restrict this down even further, right? The types of accessibility modifiers you have, like for example, in Ruby, there's only public or private. In well, actually, I think there's protected as well. I'm not sure about that. In C#, there are 6 different modifiers last time I looked. And then C++, I believe, has just public or private. And then they have friend, but that's a slightly different concept. And then Eiffel has more and different ways of doing it, so we can expose a specific set of client classes, or features can be exposed to a specific set of client classes. This is very similar to the C++ friending construct. Polymorphism, right? So as we saw earlier when we talked about polymorphism, originally when we were talking about ML, we mentioned that you have all these different ways of doing this. But in object-oriented languages, we have a specific variation, right? First off, when different classes have methods of the same name and type, right? So we have methods that when we have classes in the same inheritance hierarchy, they tend to have the same method, right? And so we know that if we have a variable of an abstract type in that inheritance hierarchy, anything under it, we can call the same methods on if they're defining that abstract type. So, for example, if we had a stack class and a queue class, right, which were both of type workList, they had an add method that we could call on them, right? But we don't necessarily know what type that is until runtime. So we don't know which one we're going to actually be calling. We just know that it's there and available. So the beautiful thing about this is this type of polymorphism allows the language to make the call on that method in the right context when even though the object may not be known, the exact type of that object is not known until runtime. And so, for example, here we use the drawable interface, which we talked about as a part of the when we were talking about inheritance and capabilities of Java and Java 2. So drawable had a bunch of different methods. 2 of them was show and hide. And basically, flash off becomes a polymorphic method because it takes in interface or abstract type drawable that then we can call these methods show and hide on, right? Even though we don't know when we define this method the exact type that D will be, right? We just know that it's it's some type that implements the drawable interface. And so this gets us to the question of, well, how does that actually work? Well, essentially what's happening is we have some reference, right? The static type of the reference may be a superclass or interface of the actual class that the object is of, right? But because types for a class are inherited, we know that it must be of type drawable. Thus, it has the show and hide methods. And so what will happen is, at runtime, the language system finds the right method for the actual class, the actual implementation. And what it's doing is it's doing what's called dynamic dispatch, right? Which is the same thing, the same kind of construct as branch on class. So it looks at the actual specific class type of that drawable, and then makes the right call as necessary. So although you can do this in Java, it's automatic in Java. This is just how it works. Other languages like C++, you can turn this on and off if you want to. This gets us to the concept of implementation versus type, right? So in some languages, this is all about inheritance, right? So in Java, we have two different types of inheritance and we have realization, right? A class can inherit from another class, or a class can realize more than one interface, or it can do both, right? In both cases, when we are extending a class or realizing an interface, we inherit the type information associated with those classes that we're inheriting from, right? So if we're extending a class, our class is of that type. If we implement an interface, our class is of that interface's type. Meaning that anywhere that our class, anywhere that we see either the base class or one of the interfaces we're realizing, anywhere that those exist in code, we can use our class that implements them in that place, right? And this is called the Liskov substitution principle. Basically, essentially, that is, we are inheriting all that type information. That's the ISA construct from object-oriented. But the interesting thing is, we can also break this down by saying, when we inherit from a class, right, we specify or extend a class. That gives us a bunch of implementation. So we inherit all the implementation from that inheritance hierarchy. On the other hand, when we realize an interface, we are only gaining the type information, and we are then being forced to implement an actual interface, a set of methods that are guaranteed by that interface. This is not always true, though, right? So how much of this separation actually can occur is dependent on the language that we're talking about. So, for example, in C++, there is no concept of an interface, right? There's just classes. And so we can either, when we define a class, we can define abstract methods, those which have no implementation. But when we extend a class, we just get everything that's defined thereof as part of our class. On the other hand, if you just want the type only, you can define an abstract base class that has no implementations, which is very similar to an interface, but not quite the same thing. But there are other things like Sather, right? Other languages where you can include concepts for like implementation from another class, but you do not gain the type information, right? Or you can inherit type, but you get no implementation, similar to how an interface works in Java. It's one or the other. So bear that in mind when you're selecting languages and the way you program in that language. On the other hand, right, when you have language like Smalltalk, which is a dynamically typed language, or Self, or Ruby, right, you have dynamic typing, which means that an object may or may not be able to respond to a particular message to a method call, right? Because there's no, although there's no compile time check. So essentially we could just execute any, call any method on there, and what will happen is, if it's a unknown method for that type, it will just throw an error. This does give you far more freedom in your programming, but it leads to an excessive amount of compile time or runtime errors, and it's far more difficult to debug. But at the same time, it doesn't really matter for polymorphism here. This type of dynamic typing and dynamic dispatch that goes on with this is what Ruby refers to as duck typing. So in conclusion, we've kind of looked at this, and we've talked about object-oriented programming versus programming in object-oriented language, and seeing that there's an exceptional difference here, right? And furthermore, we've also looked at and realized that not all languages are like Java in their object-oriented implementation, or we'll say their view on the philosophy of object-oriented concepts. The interesting thing is that there's no single object-oriented programming style or even set of object-oriented language features. I would say there's a core set of object-oriented concepts, different than features versus programming style. There is an underlying theory common to object-oriented, and that is based on those common concepts, is how we formed what's called the UML, the Unified Modeling Language, which can then be translated to any object-oriented system. But you should always be skeptical whenever someone is utilizing an underlying programming language and its features for their method of talking about what is object-oriented itself. Object-oriented is based on a much more abstract construct than what is normally presented by people who are speaking from a single language. Anyway, bearing all that in mind, I look forward to talking to you all on Monday in class. Have a great rest of your day, and we'll see you then.